Hello, this is Z5308007, and this is my solution to bonus problem number 2 for Physics 1A. So as you can see on the screen here, we are given the question of a double inclined pulley system, and the conditions are set to the right of the diagram to the left is that the mass 2 is greater than mass 1. The masses are sitting on a frictionless plane, so we don't have to worry about the friction force. The string length is a constant L, and these are under the effect of little g, which is Earth's gravity. And the first question asks us to express the string tension as a function of the masses and the angles. Now, if we go back to our very first inclined plane motion diagrams, just to the right over here, we can see that I've drawn up the two masses according to their respective force diagrams, where we have mass 1 on the left, and we can see here that we have mg acting straight down, perpendicular to the ground itself, not the plane, and we have the force perpendicular, which is perpendicular to the plane itself, force parallel, parallel to the plane, and the normal force, which is equal to the perpendicular force, just in the opposite direction. And we can see here that in our force diagrams, we can derive equations for both the force parallel and force perpendicular vectors. If we use mg here and draw up our angle for m1 alpha, because the triangle here to the left has the angle alpha, that same angle can be transposed when we draw two diagrams in between our force perpendicular and our vector mg. This also means that that angle, the sine of that angle, gives us the horizontal component, which in turn is actually our force parallel. So, as we can see to the right here, I've done the same for mass 2, and we've derived the two equations for specifically for tension. We'll only be dealing with force parallel. So over here we have the force parallel acting in m1's direction is m1g sine alpha, and the force parallel for mass 2 is m2g sine beta. Now, if you go back to our original diagram, we are dealing with the tension, and the tension is the force acting towards towards kind of the center point of the string. And so using Newton's second postulate, we know that the net force in the horizontal component which is the total forces in that one axis, is given by mass times acceleration. And so, knowing that we know the two forces that make up the net force, we know that that is tension force and the parallel force acting in the opposite direction. Now, we don't have to worry about friction because it is given that it is on a frictionless surface, therefore there is no force friction that we have to worry about. As you can see here, I've labeled equation 1 and equation 2. T minus m1g sine alpha is given by m1 times a, where a is the acceleration. And equation 2 of m2 is t minus m2g sine beta is equal to minus m2a. Now notice here that tension, we've labeled the positive sides to be positive towards the tension and negatives on the outside, which is why for M1 it is the tension force minus the force parallel, and for M2 as well it is also the tension force minus the force parallel. However, the tension force acts in the ambiguity with tension force is that it acts in both directions. Therefore, technically, for tension to work, they can't be going both in the same direction for both of the masses. So if we were to write tension force going clockwise, then tension in the middle minus the force parallel will give the net force of m2. But in this case, to make it a little bit easier for us to understand for the moment, we've labeled everything with all the forces going towards tension, which also means that either one of the parallel forces must be a negative, so that it makes sense that the tension force actually exists, because it acts inwards. And so that is actually a very important point that you have to understand, is that one of the forces or one of the accelerations is acting in a negative direction, This is only because we've defined the tension force to be positive in both equations. Either way, if you wanted to state this as M2A, it would technically be M2 G sine beta minus tension force, which is the same thing, just carrying over the -1. Now, what we do is we subtract equation 2 from equation 1 here on the bottom left, where we are given T minus M1 G sine alpha minus T minus M2 G sine beta is equal to M1 alpha, M1A minus M2A. And so if we expand that out, we get T minus M1G sine alpha minus T plus M2G sine beta is equal to M1A plus M2A. Now, all we've done here is we've applied the minus signs in. So we get a minus T here and then the minus and a minus make a plus. So you have an M1A plus an M2A. Moving down, we can expand that. We can simplify this a little bit further. On the right side, we can take out the factor constant of A, as both M1 and M2 are multiplied by A. And on the left side, we see that the tension force cancels out because we have a positive T and a minus T. So that we are left with M2G sine beta minus M1G sine alpha is equal to A M1 plus M2. Now, since it's in that form, we divide both sides by M1 plus M2. And if we take out the common factor on the left side of G, we are given A is equal to G M2 sine beta minus M1 sine alpha, all over M1 plus M2. Now we have our acceleration. Now this will work true if you sub it into either one of the original formulas for tension, because tension across both masses in this case will be the same. And so we want a universal definition for tension according to both the masses and both the angles. So we substitute A into equation 1, let's say, to solve for T. Now equation 1, we are given T minus M1G sine alpha, remember, is equal to M1A, but this time we've substituted A for what we just calculated. And so we have the M1 times G, M2 sine B minus M1 sine alpha divided by M1 plus M2. Now, if you just follow this arrow all the way to the right past the dotted lines, you'll see the continuation of the tension calculation. Now, all of this seems very confusing with a lot of M1s, M2s, sine betas, sine alphas, but don't worry, we'll work through this step by step and it'll become a lot clearer. So the first thing we did here on the top row, the top line, is we multiplied M1 to G, because since they're both constants, you can keep them on the outside for now, and we'll redistribute that a little bit later, which means we can then, to get M1 plus M2 on the other side, we multiply both fractions by M1 plus M2, cancelling out on the right side, giving us T minus M1G sine alpha in brackets, multiplied by M1 plus M2 is equal to M1G brackets and all the rest of the M2 sine beta minus M1 sine alpha. Now what we did on the second row is we expand the brackets to the left, therefore we multiply everything across each other using FOIL or any other method you know of. So we're given Tm1 plus Tm2 minus M1 squared G sine alpha minus M1 M2 G sine alpha. And all we've done there is multiplied the T across the M1 and M2 and also multiplied the minus M1 G sine alpha across the M1 and M2. And on the other side, we've done the same thing as well to see if we can find any like terms. We've multiplied the M1G across to M2 sine beta minus M1 sine alpha. And so on the right side, we are given M1 M2 G sine beta minus M1 squared G sine alpha. Now notice here, doing that, we are able to find a common term where we have a minus M1 squared G sine theta on this side, and also another minus M1 G squared sine alpha on the other side. We know that if there's a minus on this side and another minus on the opposite side of the equal sign, this carrying over means adding. Therefore, both of these will cancel out on both sides. And we do exactly that. Onto the third row now, we have Tm1 plus Tm2 minus M1 M2 G sine alpha is equal to M1 M2 G sine beta. Now, let's move the M1 M2 G sine alpha to the other side. We're left with Tm1 plus Tm2 is equal to M1 M2 g sine beta plus m1 m2 g sine alpha. Now, remember the first time around where we have this tm1 plus tm2. They have a common factor t. Therefore, we can take the constant out and put m1 plus m2 in brackets. Now it looks like a nicer form like this, just on the bottom. T out of the brackets, m1 plus m2 is equal to yada 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 on the other side. Now, to simplify the right side as well, have a look at the terms we are given on the right side. We have here m1, m2, g sine beta, plus m1, m2, g sine alpha. Now notice that both of these have also a common factor of m1, m2g on both terms. Therefore, we can take that g, m1, m2 out of the brackets and put sine beta plus sine alpha in a bracket. And now, since the other side we've also done that, we can divide over the m1 plus m2 onto the other side to give us the equation for t, where t is equal to g m1 m2 divided by m1 plus m2 multiplied by sine beta plus sine alpha. Now, I've just decided to put the sine beta and sine alpha just on the outside, but technically it all falls under the same m1 plus m2. It's just a little nicer to see where all the components went. And so you've got all the constant factors out, gm1, m2 on the top, and you've got the other m1 plus m2 just underneath it, multiplied by what we are given left with sine beta and sine alpha. And there you have the expression of tension in a function. And now we're moving on to the next image, which we are told to determine a condition for where the masses are at rest or in uniform motion. Now, at rest means zero acceleration, or both the net force of m1 and m2 will equate to each other. Now, if you don't believe me, you can have a look at this calculation down the bottom. If we rearrange our initial tension equations to substitute a to 0, we know that, well, for number 1, t minus m1 g sine alpha is equal to m1a. Therefore, we divide both sides by m1 and then substitute a to be 0. Therefore, t minus m1 g sine alpha over m1 is equal to 0. We do the same thing for m2. m2 g sine beta minus t over m2 is equal to 0. Now notice how it's now m2g sine beta minus t. This is because from the equation we had a while ago, the t minus m2g sine beta was actually equal to minus m2a. Therefore, we just carried over the negative 1, turned it into m2g sine beta minus t, and then we moved the m2 across. Now rearrange all this, and you'll find that the tension force is equal to m1g sine alpha, which is also equal to m2g sine beta. Therefore, for an acceleration is equal to 0, the case in which our masses are at rest or uniform motion is when m1g sine alpha is equal to m2g sine beta. And like I told you at the start, it's when both the net forces equate to each other. Because it makes sense. If the force going for m2 is the same as the force going for m1, then they're not going to accelerate. They're going to be stationary. However, remember there's a catch. At the start, we already know that the condition m2 is greater than m1. This was the whole premise for the tension force we calculated earlier. Because if you go back into our early equation for acceleration, have a look down here for tension. Have a look for the acceleration force. If m2 sine beta is equal to m1 sine theta, well, you're taking the difference between those two to find acceleration. Therefore, it'll be 0. Anything multiplied by 0 is 0, which makes sense. However, in the case we're given, m2 already is greater than m1. Here's the issue, because there aren't any numbers given, we're only given terms. This means that m1g sine alpha equal to m2g sine beta will only work if this holds true. Note that we can also neglect the gravitational constant, because we can also just divide that across and cancel them out, where m1 sine alpha is equal to m2 sine beta, where the angle alpha must compensate for m2 being greater than m1. Therefore, m2 sine beta is equal to m1 sine alpha when alpha is greater than beta. Now, this makes sense because we can see that if m2 is already greater multiplied by sine beta, then whatever value m1 is, And even if sine alpha is the same angle, the factor of m2 being larger than m1 already means that it's going to accelerate according to the m2 and the mass 2's direction. Therefore, to actually compensate for the fact that mass 2 is already greater than mass 1, the angle of inclination for m1 can then allow this equation to equate to 0. And there you have it. There is the solution to bonus problem number 2.